Ayubowan duwe pute. Welcome back to my channel again. Today's lesson is on real numbers. In particular, we are going to have a look at surds and also mathematical operations on surds. Therefore, today's lesson will be quite important for you. And then also we are going to connect this one to future lessons that we are going to learn. Without further ado, let's start the lesson and work our way through. The learning intention for today's lesson is to look at number sets and then surds, also arithmetic operations on surds. Let's have a look at the number sets. The very first set that we are going to look at is called natural number set, represented by letter N and with a line in the front here. This will have 1, 2, 3, 4 and so on. And I have put 3 dots here. What it means is this goes forever. Basically, it keeps increasing. This is what we call natural number set or the set of natural numbers. Simply, we call them counting numbers as well. The set of natural numbers. The next one that we are going to look at is an improvement on this. We are going to consider this set and also the negative values of these and also 0. This is what we call the set of integers. So integer number set. These are integers. And you can see now the natural numbers are inside the integer set. Well, the next one that we are going to have a look at, let me pull a different color, is called rational number set. Rational numbers. What are the rational numbers? Well, rational numbers are of the form x over y such that x and y are integers, could be positive or negative, but y cannot be 0 because you can't divide numbers by 0. So that is our definition. Or we can write down this is x on y form where x is an integer, y is a positive integer. Okay, let's have a look at what the positive integers mean. The positive integers mean basically the natural number set. Every number is starting from 1, whole numbers 1, 2, 3, 4 and so on and so forth. Okay, so we have an understanding on that one now. Is that all we have? Let's think. If you can find a number that can be written in a different form, or rather let's say we can't write them in this form, the given form, then if these are called rational, the ones that we are going to consider called irrational. Well, you've probably seen these numbers before. Let's have a look at square root of 2 or maybe pi. Okay, what is the square root of 2? You can write down 1.414, first 3 decimals, and here 3.14 up to 2 decimals. But what we can show that is we cannot write these in the form of x on y form as we seen before, which means these are called irrational numbers. There are many more. In fact, you can write down this. Have a look at this one. What is this? What is this? This is called cube root of 2. This is called cube root of 5. They are also irrational numbers. You can't write these quantities in the form of x on y as we seen before for rational numbers. Well, now let's have a look at just a number line here. Let me get the number line. Can even put some arrows. So that's there, and I can say right here 0, and this is 1 and 2 and 3 and so on and so forth, and here -1, -2, -3 likewise. Now if you take any form of x on y, goes somewhere. Let's just do a quick trial and error. 7 and 2. Okay, 7 and 2 can be positive or negative, doesn't matter. Let's say positive. This is in fact 3.5. Where's 3.5? Look, it's right there. The reason is 4 is here. It's exact halfway through. We can pull another quantity. Let me pick another color. Let's say -9 on 4. What is -9 on 4? Well, 2.25. So therefore it is right here, just right in the middle there. Okay, so we get a feel how they set into the number line. Are they the only ones? Well, not really. The root 2, that is 1.414 as I written, just the approximate up to third decimal. Well, that one simply just here before 1.5. Well, if I have root 3, which becomes 1.732, that goes in here, just a little bit less than the midway between 1.5 and 2. And you get the understanding. Now let's represent these ones in a Venn diagram. So you have seen Venn diagrams before. What we are going to do is we are going to represent these in a Venn diagram. Let me put these together. Now if I look at all the rational numbers and all the irrational numbers, that's what we call real numbers. Let's write that first. Real numbers. So that is our whole set, or the universal set in this case. Therefore, what we can do is we can draw a box in the Venn diagram. We can write down that's our real number set. That's our R. And then we can represent each of these inside. So let's indicate this one in green as rational number set. Well, if it is rational, what is outside? What is in here? It's actually complement of Q, isn't it? Do you remember that from our sets lesson? Complement, outside the rationals. And inside the rationals, we can find another set. What do we find? We can find the integer set. So we can write down that in red here, integer number set. Then inside that, the smallest one that we learn here is the natural number set. Right there. So that is our natural number set. So first set of natural numbers, set of integers, set of rational numbers, and then outside we have irrational numbers such as root 2, root 3s, and so on and so forth. Inside we do have here -3. Here you have 1, 2. Likewise, 0 is out here. And then here we have 1.5, 1 on 3, likewise. Now you get the basic understanding of the sets. Before we moving into surds, let's have a quick look at on decimals. I'm going to go into the right here to work on decimals. I'm going to discuss a few things that we learned just then. Okay, decimals. Well, let's write down some decimals. One of my favorite numbers, 6, is a perfect number. 6.000. Then also I can write down, let's say, a quarter. What is quarter? 0.25000. Likewise, it goes. Everything is 0 after that. Well, the other one I can consider is 1/3. What is 1/3? 0.333. Keeps going. Another one, 23 on 9. What is 23 on 9? 2.555. Likewise, keeps going. And then let's consider two more. Let's say 27 on 11. So that becomes 2.454545. Okay. The one last that I would like to write is 47 on 7. This is 6.714285, and then again 71485. You can see that block repeats the set of numbers in here, the digits 714285. That is the one's going to repeat here. What is the difference between these decimals? The one that I'm going to consider here on the top, the first two, and then the last four. What is the difference? Well, this is ending with 0. 0 is repeating. Therefore, we call these ones finite decimals. Finite. Or we call them terminating decimals. We can call them terminating decimals. Then what are these then? They reoccur. So we call them recurring decimals. We call these recurring decimals. Now, Due Pute, you have a better understanding on what are finite decimals, what are recurring decimals. Well, now what we can do is we can simply truncate these and write down the shortened form here. Call it concise form. We are going to call this form as concise form. Let's write down. We can write down 0.3 and you put a dot. That indicates the number 3 repeats. Next one, 2.5 is repeating. Therefore, dot on the 5. Here, 2.45, both of them are repeating. Hence, we have to put a dot here and a dot there. What it says is this block is repeating. How about the next one? Well, I have to put this bracket a little further here. We can write down 6.714285. That is the block which is repeating. Hence, I put a dot on the 7 and then dot on the 5. What it says is everything between these two dots, 7 to 5, that block is going to repeat. So that's how I write down concise form. Before we move into the surds, let's have a look at another or maybe two quantities that we just seen before. Let's say square root of 2 and then also pi. Well, how do I write down square root of 2? 1.41421356. This keeps going, never stops. Likewise, pi 3.1415925. This keeps going as well. If you look at these two quantities, their decimal representation doesn't have a block that repeats like we've seen before. So there is no recurring block in either of them. Therefore, we call these ones an infinite decimals. So these are called infinite decimals. Simply because it doesn't have a block that repeats where we can put as a recurring decimal. So it is not a recurring decimal. Okay, let's move on to the surds. We are going to have a look at surds quickly, and then we work through our examples using the theory part that we are going to learn simultaneously. Well, if you look at the four quantities that I have written, you can clearly see the last one asking the square root of 36, which is a positive integer. I get as 6. Therefore, 36 is called a perfect square. That's why we get a positive integer as the answer. But none of these would deliver that to us. Their square root is not a positive integer. Well, you've probably seen this one before, this radical sign. In case if I did not get a positive integer as an answer for my square root, or maybe even cube root as we've seen before, for this particular case, we call this one a surd if it doesn't deliver a positive integer. What do they give us then? Well, they will give us a decimal which is an infinite decimal. We can of course round off to the first or second or third decimal place value, but we would not get a perfect integer as an answer. All right, let's move on and then have a look at some theory work on here. First, we are going to have a look at these surds. Now, one thing that we need to remember here is called entire surd. So if you look at the two examples we did before, one was root 2, the other one was root 12. Well, root 2, you cannot simplify any further. Now have a look at the root 12. Root 12 is written in this manner as well. 12 is 4 times 3, where I know that for the square root of 4, I have a good answer, positive integer. What is that? That's 2. So therefore, this is 2 root 3. In fact, the starting point here, root 12, is in fact 2 root 3. Therefore, if I have the full number inside this hat or the radical sign, we call this as an entire surd. So here we have entire surds to be simplified into surds like these ones. Okay, let's have a look. Now, before we move on, let me write something here on the side. 1 squared, 2 squared, 3 squared, 4 squared. Likewise, if you can write down or remember this one, up to 12 would be good. If it is up to 15, that's great. So there are a couple more in here, 169 and 196. Well, why do we need those? I'm going to zoom in here, zoom out so that we can see them. Well, 20 can be written as a perfect square and another number. That's the only way we can simplify. We always need to find a perfect square out of this area here. Well, 20 is in fact 4 times 5. What is the square root of 4? 2. Therefore 2 root 5. You get the point. Now, next one, root 48. What is the highest perfect square here? That is in 48 as a product with another number. Well, you can say 4 times 12, and we have seen 12 is going to get simplified further. Therefore, there is another number. Well, can't be odd number here. The next one is 16. In fact, it is 16 times 3. Square root of 16 is 4 root 3. The middle step which I bypassed here is in fact the one in blue, root 16, it's very tiny 6, and root 3. There's a multiplication here in the middle. Root 16 becomes 4 and root 3 itself. Well, now you know the point here. You understood. Let's move on. 150, 25 times 6. That becomes 5 root 6. 300, very easy. 300. I know the 100. It becomes 10 when you take the square root. 10 root 3. Well, we're going very fast, which is great. Feel free to stop the video and work your way through and cross-check with my answers. Well, now we're gonna go back. Earlier we simplified from entire surd down to a simple. Now just a surd given. Now we're gonna put it back. Well, how do I put that back? Under the hat. Well, root 6 is here. What is 3 in terms of a root? Well, what root is 3? That's 9, isn't it? There's a 9 times 6, 54. Therefore, square root of 54. Now we have written the surd as a entire surd. Let's do the same here. Put a different color. Second section here. What do I write for 7? What square root is 7? Well, 49. That's why we need to remember these perfect squares. 49 times 2, 98. The easy way to multiply, 2 times 50 is 100. Take 2, 98. Final one on this set. 10 is square root of 100 times root 5. What you have to remember, Duepute, you are only changing the number, the integer in the front here, to a surd form. So therefore we are moving in here with a multiplication 500. So little things to remember. Okay, well, now we are going to simplify. Okay, this is what we call collecting like terms. Collecting like terms, here we have 1 root 6, here I have 7, altogether 8. And then I have to take away 3. What is 8 take away 3? Well, that's 5. 5 what? 5 of root 6's. So I left with 5 root 6. Next one, you can see when I underline, or rather, 4 root 7 take 3 root 7. Well, I end up with 1 root 7, isn't it? And then the rest are 8 root 5 and a 1 root 5, altogether 9. Take 2 root 5 is 7 root 5. So that's my answer. In this case, root 5 and root 7 are not like terms. They are not like terms. Therefore, you can't put them together. Just leave the answer like this. This is your final answer for this problem. Okay, another one on this set. I have root 11s. Well, I'm looking for root 11s. There they are. 9 and a 6, they both adding. 15 root 11. Here I have 11 root 3's, and then I take 6, that gives me 5, and another 5, that gives me 10. So I have altogether 10 root 3 at the end. So that's my answer. I'm using different colors to differentiate this so that you can clearly see and understand easily. Okay, next lot, we have to rationalize the denominator. Well, rationalizing the denominator means I need a whole number in there. So how do I make root 7 to another whole number? The easy way is to multiply by itself. Therefore, I have to multiply numerator and denominator both by root 7. That gives me 3 root 7 on the numerator, while root 49 in the denominator. In fact, I don't need to write this. What is root 49? Just 7, isn't it? Therefore, the answer is 3 root 7 on 7. Now you can see the denominator is now rationalized. It's a rational number. It's just a number. That's what it is. It's not a surd. That's what it is. Well, don't simplify back again. You will end up with having this blue expression again if you go back from red up that way. So don't do that. That's our final answer. Let's do this one. Well, I have done these 4 different variations so that it covers any variation that you could come up with in this type of rationalizing denominator problems. Well, do I have to multiply by 3 root 7? Well, not really. Just root 7 will do, because 3 is already not a surd. It's not a surd. Now what we are writing is on the numerator 10 root 7. Underneath here 3 times root 49. What is root 49? 7. 3 times 7 is 21. Hence the final answer is 10 root 7 on 21. Well, we got that through. Let's see another variation. Okay, here same manner, root 6. We are going to multiply both numerator and denominator by root 6. What do we get? We get 12 root 6 divided by 5. What is root 6 times root 6? Root 36, which is a 6, isn't it? Okay. Now you can see this is similar to fractions. There's a 1 6 here and 2 of them. They cancel, hence delivering the answer, the final answer as 2 root 6 on 5. Okay, one last one. Here we have surds on both numerator and the denominator. So we multiply top bottom both by just root 11 duwe puthe. We don't have any issues with root 3 because it is on the numerator. So be careful with that. Now what do we have? 5 root 3 times 11, 33. You have to make sure that you multiply each of these surds only, just them. You are not multiplying 11 by 5. It's a number outside the surd. It doesn't affect inside. The next one, 2 times, what is 11 times 11? Well, if it is root 11 times root 11, let's have a look at what we've seen so far. Root 3 times root 3, root 9, 3. Root 7 times root 7, root 49, 7. Then what is root 11 times root 11? Has to be 11, isn't it? Therefore 11. Therefore the final answer here we get is 5 root 33 on 22. Okay, so we done them all. Now we are moving into multiplication. Well, what you have to remember is numbers multiplied together, surds multiplied together themselves. Therefore, let me get different colors. That's easier. So 2 colors here. So I have 2 times 3 is 6. and 5 times 7, 35. I have differentiated this one in colors so that it's easier to understand. Here we have root 7 times 11. Therefore, we have 3 root 77. Let's move on to the division. Let me write them. One on the numerator and the other one in the denominator. We cancel the numbers, and then also we cancel the surds separately, and you have to be careful when we write. What we get is 3, then the surd is 3 as well in this case, root 3. Next one, 10 root 5 on 2 root 15. So you got to be very careful on this one. Well, 2 and 10 get cancelled and delivering number 5 on the numerator who has a number, and then this 5, let me get a different color, this 5 and 15 cancels and gives me root 1 on the numerator and root 3 on the denominator, hence root 3 in the denominator. So 5 on root 3. I can even rationalize this one and make root 3 is there, and then the answer becomes 5 root 3 on 3. So if the question says simplify and rationalize the denominator, that's what you need to do. Okay, that's our purple answer is our final answer. Okay, one more. Root 98 divided by 4 root 2. Here we have 1 and 49. It's root 49, therefore we write down root 49 on 4, which is 7 on 4. That's my final answer. Let's keep moving. The final set that we have, of course, we have 4 of them to complete. Let's see how fast we can do this. As you can see, this is an entire set which needs to be simplified. 4 times 2, that gives me 2 root 2, and I know that I have a number 3 in the front, and root 8 is 2 root 2 itself, plus 2 root 2 plus 4 root 3, and like we had before, what is root 12? Well, root 12 is root 4 times 3, therefore 2 root 3, hence 2 root 3. Now I have, get this color, 6, 3 times 2, 6 root 2's and a 2 root 2. Here 4 root 3 and then 2 times 2, another 4 root 3. Well, what is 6 and a 2? 8 root 2, 4 and a 4, 8 root 3. That's our answer. Well, let me use different colors in the next one to get a nicer view here when we write. Okay, here 4 times, can you do this in your head? That's in fact 7 times 4 or 4 times 7. Then this is 2 root 7. The reason is root 4 is 2 root 7 itself, minus 3 root 7. Here plus 6 times, what is root 11? 44, it's 4 times 11. 11 goes in there, therefore 2 root 11. Plus 99, again root 9 times 11, therefore 3 root 11. Here we have 4 times 2, 8 root 7's, take 3 root 7. Here we have 6 times 2, 12 root 11 and 3 root 11. We have 8, take 3, 5 root 7, and then we have 12 plus 3, 15 root 11. I hope now you get the hang of this one. let's move on. It's another variation. I have included all the variations that you could come up in an examination. So therefore, if you complete all these and get the right answers with me, you are fine. Here we are going to look at 3. What is 48? Well, 16 times 3, that gives me 4 root 3 minus 2. Here we have root 9 times 3, that gives me 3 root 3. Square root of 9 is 3. And this one I need to multiply both numerator and denominator by root 3 to rationalize the denominator. Hence what I get here is 6 root 3 on root 3 times root 3 root 9, which is a 3. Now you can see we are doing things in our head as well, just to make it quicker. That's what you need at the end anyway. Let's write the next step. 3 times 4, 12, root 3, take 2 times 3, 6 root 3. Now you can see these get cancelled, and we have plus 2 root 3. They're all in root 3s. They all like terms. 12 take 6, take away 6, 6, plus 2, 8. So the answer is 8 root 3. Okay, part D. Little tricky, challenging, isn't it? Well, this is 2 root 7 itself. What we need to simplify is this one. So you need to crank your brain and see what numbers go into 252. Well, if this was, there's a clue here. If this was 7, this should be done with 7. So let's give it a shot. How many 7s in here? Well, I have 3, 21, carryover is 4, 42, oh, 6. There you go, we get it. So 36 of 7s in there. Is that right? Well, we are right, aren't we? Okay, then we write root 36 is in fact 6 root then 7. Hence, this becomes 6 root 7 on 3. So that's our working for square root of 252. What is this? Ooh, 1 3 there, 2 of them. Well, I got 2 root 7 minus 2 root 7. What is the answer? Well, answer is 0. Okay, we learned a lot today on real numbers, in particular surds and mathematical operations on surds. I do hope that you gain a good knowledge on that. Please retain that knowledge for future use. We will be connecting and definitely using this knowledge in near future. I'm planning to do another video lesson very soon. Until I see you there, I would say Ayubowan, Teruwan Saranai.